Perfect. Okay. Welcome everyone. If you cannot see the whiteboard for some reason, please let me know, okay? So that you can see what is wrong. Otherwise, we are all expected to be seeing it. Now, we've discussed a couple of things since we started our machine learning program. We talked about, in our previous class, we were looking at bias and variance. And we tried our best to try to explain this concept of bias and variance, wherein we said bias is a situation whereby the model performs poorly during training and testing, and it also performs poorly during testing, right? And we say for variance, this happens when the model performs well during training and poorly during testing. And we try to give quite a good reason, some reasons why this would happen, right? And we said this comes as a result, bias comes as a result of underfitting, that's high bias. And this one can come as a result of what? Overfitting. And we try to give some of the reasons why we can get overfitting, right? We said overfitting can come as a result of, what were some of the factors we say about overfitting? We talked about pre-processing data leakage. You remember we talked about this where you with one code encoding, and then we talked about target-based data leakage, where we were giving one column has almost the same information as the target-based data leakage. And then for bias, we said that for bias, some of the reasons why you would have a model performing poorly during training and during testing is that one is small amount of data, like your data is the data you're using for training, of course, that's what we know. The data you're using for training is small, and then you have small amount of data, and then you have unclean data. If you didn't clean your data well, unclean data, right? If you didn't clean your data well. So in this case, we are talking about the data quality. Data quality, that would be the right word. The quality of your data. So if you didn't have good data, then your model will not understand. And there is something now that is generally known, and he said that simple models, I'll explain this, and this is where our class of today is going to tend to have high bias. And complex models tend to have high variance. Now let's say a few things here. This is part of our class today. We can focus on this. And what we're saying is that simple models tend to have high bias. Why high bias? And complex models tend to have high variance. Let's keep this one, complex models, and focus on simple models. An example of a simple model is a linear regression model. Linear regression is considered an example of a simple model. The reason why they call it simple is because the mechanism of action is very straightforward. And in other ways, you say it's simple, right? In another sense, you say simple. An example of a complex model, you have something like a decision tree is a complex model. Decision tree is an example of a complex model. And again, they tend to overfeed. And the reason is because, again, you look at, once we look at decision tree, you understand that the mechanism of action is a little more complex, because we'll start talking about entropy and information gain, which will be what a decision tree functions based on. And there are other models that that have their different ways of functioning. So these are just, again, some of the things we are trying to look at. And so now let's talk about the decision tree. You remember we already talked about how a linear regression model, please. Let's talk about a linear regression model. I remember how we said a linear regression model functions. A linear regression model functions by plotting a line of best fit amongst your data points. And like we said, the line of best fit is the line where the error is minimum. We already said these things. Now, there are some assumptions. For a linear regression model to work very, very, very well, there are some assumptions. What we are saying is that, one, the first assumption is that there is linearity. Linearity. What does linearity mean? It means there is a linear relationship. There is a linear relationship between the features. The feature in this case is feature, not features, because we're still talking about simple linear regression, and the target. When we say there is a linear relationship, what we are saying is that the relationship either is like this or it's like this. So there should be some sort of a linear relationship. So a situation where your data is like this, where you don't have the data going either like this or coming like this, shows that there is no linearity in this data set. There's no linearity in this data set. So if you had your data like this, your points plotted like this, maybe you can see there is a positive linearity. Or if the points were like this, maybe you have something like this, then you can see there is negative linearity. But if it is like this, where you don't know whether it's lying to the right or to the left, we can say there's no linearity. And when we do the correlation, when you remember, the correlation here should be something around 0. Here will be negative, here will be positive. We already discussed this in our previous class. Now, so that's the first assumption as far as linear regression model is assuming that there is a linearity, between the target and the feature. Is that clear?
Yes, sir.
Okay. The next one is that there should be what we call there should be no autocorrelation. No autocorrelation. This is the second assumption. No autocorrelation. And now what we mean by there should be no autocorrelation is that there should be no relationship between the errors. The error between, because remember our line of best fit, we calculate the error. So we are saying that the error between this point and this point should not be related. There should be no relationship between this point and this point. We are saying that there should be no correlationship between the error, or we call it the residual. That one I cannot overlay emphasis on it. I'm just saying there's no correlationship between the residuals. We already know what the residual or the error, right? Then the next one is that number 3,
Sorry, Prof.
which is the third assumption.
No, Prof.
Is there a question?
Yes, please, I don't understand this last one, the no autocorrelation. I was trying to follow, but I couldn't get it.
I'm saying that if you plot a point like this, there's the best line of best fit. You have the line of best fit. There is an error between this point. The error, this is the error, this is error, this is error, right? We already know how the actual minus the predicted. We are saying that if you plot these errors against each other, there should be no relationship. That is what we call autocorrelation. If you plot the errors, you should have some data like this. They should not show any relationship. The data should, that means maybe if you run the correlationship, maybe for example, you have something around 0. It should not show any correlationship between the errors. Does that make sense?
Okay.
There should exist no correlationship between the errors. That's an assumption for the linear regression model. It assumes that there is the data that you're giving it. If I take the errors, anytime I do a prediction and I take the errors and I plot them, I'm not going to have any correlationship between the errors and the feature. There's no relationship. So if they plot it, and maybe you run the correlationship, you should have something around 0. The next thing we are saying is that there is number 4. Is it number 3 or number 4? Number 3. Number 3 says there's what we call homoscedasticity. 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 What is homoscedasticity? Assuming I plot the error, I guess maybe the feature, I don't know what the feature was. Maybe let's call it a C or something. So assuming, and I said there was supposed to be no relationship, so I'm expecting to get data like this. This is data that doesn't show any relationship, right? So if I put a line here, this shows that there's no homoscedasticity and it shows no relationship. Of course, you can see that. But then let me show you a situation where there's homoscedasticity. Where this shows that there is homoscedasticity. And let's show a situation where there's no homoscedasticity. If I do that again, you can see a situation like this. So if I plot this point again, let me just draw this line that's drawn like this. Now, what is going to happen is you can see something like this. The points around this line. Now, when you look at these points, maybe let's say let's draw these points like this. These are the points. Assuming that here, the points now are around the line like this. The distribution, the focus on the distribution of the points around this line. And then again, it can come all back like this and you have the points scattered again more like this. So if the distribution is not uniform around this line, there's no homoscedasticity in this data set, right? Because of this. So if you just go to your browser, for those that are, let me stop sharing here. Let me stop sharing. And if I share from this other screen of mine and just quickly do a browse, if I show you images of homoscedasticity online, you should, can you see my screen?
Yes, we can see.
Yes.
Let me see homoscedasticity. But pull this up. Sorry, my network is a little slow. Let's give it some time. These are very pertinent assumptions, so you're gonna need to understand. So it says homoscedasticity is a statistical, oh shit. Hold on. Say homoscedasticity is a statistical assumption that the variance of a sequence of random variables is same. So
Please sharing that window.
I'm not sharing my whiteboard. I'm sharing a a Chrome table. I mean, you should be seeing something I'm moving with small charts on my screen and some AI output. Is that what you're saying?
Yeah, it's not sure. I can see Google, you're on Google, you typed in
Yeah.
So
Yes, that's what I wanted to show you. Images of Homo sedacity so that you can see what I'm talking about. So yeah, this is a good situation of Homo sedacity. Let me open this one. I hope it open and they don't start showing me some adverts left and right here. Oh boy. Don't start asking me to validate anything. It's just an ordinary website I want to log into a back. Okay. So you see there is so this is, if you look at the way they have labeled it, right? They labeled heterosedacity and homosedacity. And if you can see from my screen here very well, this is a situation of homosedacity. And you can look at the distribution of the data points, right? And then here, look at the distribution here. It doesn't look normal. There's this indentation here like this, right? And here again, if you look at the distribution of the data from this end, it's higher, and then here everything just goes down to plunge. And so we are saying that in a linear regression situation, right, it assumes that there is homosedacity between within the variables, right? There is no, at first there is no relationship, because if you look at this doesn't show any relationship, of course. Because if it were supposed to show linearity, you know that linearity, we already said linearity will be data that looks like this. It's in this direction, or it's in this direction, the data is in this direction. Oh, that's linearity. But if you have your data running straight like this, it doesn't show any relationship. So you can't, that's already clear that there is no relationship. So this is a situation of homosedacity, and this is hetero, meaning that it's not homo, of course. So I just wanted to show that distribution to make that clear. That's an assumption. Like I said, it's an assumption. It assumes this. Is that clear?
Yes, sir.
Let me stop sharing again, and then I come back to this on the screen again. Let's continue. I'm building a case, so once I am done, it's going to take me into something else now. Now we're going to look into it. So there are possibilities that you can actually test all of that and check your data whether there's homosedacity by just running those plots against each other. We can get that going. If we have time, we can do something. We can have something like that. But I don't know if time is going to permit us to work on something where we have to work on homosedacity, test homosedacity, and all of that. But if we do, we can look into it. Okay. So I've talked about homosedacity. Again, normality of residuals. Again, when you talk about when you plot the residuals again, when you say it's normal, that means it's going to be something like this. There's no how did you call it? It's not skewed, right skewed or left skewed, right? You remember the other day I was telling you guys about skewness. There's nothing like this, or there's nothing like this, or there's nothing like this. I don't know. Oh, man, this one's bad. It's terribly bad. There's nothing like this, and then you have something like this. It's not skewed in that way, so that's just what we're saying. So normality, right? That means the distribution around the mean or the median, depending on which measure of central tendency you're using, is the same, right? It's almost the same. There's never no perfect normality. So yeah, these are some of the functions. These are some of the assumptions that come with linear regression. And so now, given all these things we have said, given all these things that we've said, now the question you're going to be asking me is what's that? We've said all these things that it assumes all these things. It assumes all these things. So that explains why we said by default you have a model like linear regression exhibiting linear regression. You have it exhibiting something like high bias, because it's rare that you have all these things being made, right? All these assumptions being ever written to true, right? So that is why you definitely get to see situations of high bias. And again, we can now look at different ways to try to correct that in case you have your data and that's not working. Or in the case where you cannot correct it, then you have to resort to another form of model, which the right thing to do is always to test these things out before choosing a model, right? And you are supposed to do this during your exploratory data analysis. You're supposed to do this during your exploratory data analysis, and you can do this exploration. And as you do this exploration, now you choose your choice of your algorithm, whether you're going to be going with a linear regression model. And for regression problems, we know we can use if your linear regression model is not giving you the expected result, there's logistic regression that comes into play, right? Which is one of the algorithms we're going to be looking at immediately after we are done with all these small topics in between that we want to handle. So is there any question so far? Is there any question so far? Okay, in the absence of that, I take no silence as silence to mean no, that there's no question. Okay, now let's have a discussion. Let's have another discussion. So I just wanted to make these assumptions clear so that there should be no confusion somewhere along the line, or getting some people confused about some stuff there. So that when you come across that information somewhere, it should throw you off balance. Okay. Now we talked about linear regression, and we said when it is simple linear regression, we'll have a situation whereby you have your equation being something like y equals to mx plus maybe b. We've talked about this, where this is your gradient and this is the intercept. The intercept is where it cuts the y-axis. And this is for a case where you have just one feature, right? Like you are just using salary age or your GPA to predict your salary. Like we did this GPA. So X here stands for your feature, which is your GPA, and Y is your target, which is your salary. Now, in a case where you are predicting salary now with more than one feature, now this leads us to what we call, this is simple. Now it takes us to a situation where what we call multiple linear regression. And in that case, then now you have a situation where you can have y equals to mx1. You can have mx1, 2, 3, x3, x4, right? Plus b, right? You can have multiple x variables, right? mx1, mx2, mx3, mx4, because x now becomes multiple variables, right? So when you find yourself in a situation like this, and in our last class we said the metrics that the simple linear regression used to fit the line of best fit, we said in our class that it was OLS. And you remember in that we said there were three options there. We talked about OLS, we talked about gradient descent, and the other one was or what was the other option again? There are three of them. When it comes to my head, I'm going to add that. But then, because this class we are going to be talking about gradient descent, so the third one I've just skipped my mind. So you have OLS now, and you remember for the OLS, I told you that I said that for the algorithm to be able to get the best value, because remember the equation is y equals to mx plus b, where m is the gradient and b is the y-intercept. I said that when you have the equation of the error is y, is where you have error, is where you have your error your error being equals to a summation of y minus y bar. And y minus y bar becomes your predicted, and then your y becomes your real value. And so if I replace y here by this, then we are saying that the error becomes an equation of mx plus b, all of this minus y bar, right? That's what we say. And so you notice that the equation of the error becomes an equation of m and b, right? And so that's why we ended up and saying that for you to get the equation of the line where the error is the least, where the sum of error, like this value, is the least, you have to get the value of m and b where the error is least. And we said it starts by plotting error E against m, keeping b constant. And so it does, and you get a parabola like this. And so this is the error, and this is the point where error is minimum. I get the corresponding value of m. It does the same for error against the error now becomes error against how do you call this? Now b, and then this becomes the error. It does the same thing, right? And then it gets the points of b, the value of b where the error is least, right? So you get the value of b here where the error is least, and that's how it fits that value here and gets the line of best fit. Now, when we come down now imagine the situation that this is where the equation of the line, this is where your equation of the line looks like. Now look at the situation whereby, and so here you have what we call is this a convex function? If I'm not getting the word wrong. And when you have a situation where you have a non-convex function, this is convex function. Now you're going to have a situation where when you plot this plot, you're going to have something like this. You're going to have something like this. And you notice that in this situation, you'll find yourself having multiple values where the error is least, right? Multiple values. And so when you have a situation like this, how do you solve this? You notice that if you're supposed to use OLX, this is going to fail you. You cannot do OLX here because otherwise the computing power, if the computing you need to be able to run this will be too high, because this might even have as many as possible, right? You have multiple minimum points. So how do you solve this problem? That is where the gradient descent comes in. And you have this when you're dealing with multiple linear regression at times, when you are having a function like this. You get it? So when you find yourself in a situation like that, that's where gradient descent comes into play to be able to get the line of best fit, right? That's where gradient descent comes in to get the line of best fit. And how does gradient descent works? How does gradient descent works? Now, what it does is that, let me get this one nice example I had somewhere. Give me a minute, let me pull it up. I have one very nice example that I used in one of my lectures somewhere. Is this where it is? Did I? Decision tree gradient descent. Okay, I think this should be. I'm hoping this is. So now, what it does is that, I was tempted to come and do gear all. Let's look at the situation. So what it does is that for gradient descent, it starts things you cannot see, like I explained. For example, let's assume that this was error against B. it can't pick any of these, right? It can't pick any of these. So what it does is that it starts with a random value of b. It just picks any random value of b. It can be any value, okay? It can be any number. It starts with any random value of b. And then from this value of b, the algorithm checks the value of m. And if the direction is negative, the algorithm increases the value of b. Let's do that. Let's do that. So let me just let me just pick this one loop here. Okay, let's not complicate the whole thing. So I'm just going to pick this one loop like that, and then I'm going to plot something here like this. So I'm just picking the first loop, and let's pick it like this. And so let's say this is our error against b. And remember, I said for OLS that it keeps m constant and then plots error against b. And after that, it keeps b constant and then plots m against e. So it's the same thing. So here, what it does is that it will pick a random value of b. Let's assume that this is our 0 and 1. So let's say it picks b as 1. So what it's going to do is that it's going to come up here. It gets the corresponding point where b is, and it calculates the gradient at this point. It's going to calculate the gradient at this point. How do you draw the gradient? The gradient should be some sort of a tangent against. It's going to draw a line like this. How do you calculate the gradient at this point? I'm trying to draw a line that shows the gradient here. So if you want to calculate the gradient at the point where you have B meeting, this is the point. So you calculate the gradient. Or when we say the gradient, please, we are talking about the slope of the curve at this point, the slope like this slope is what we are calculating. So that's what we refer to as a gradient here. So it calculates. So what it will do is that it will change. It will pick a random value of b. And mind you me now, if you calculate the slope here, how do you calculate the slope? You take the change, right? So if I do this, I'm going to go here, right? Let's assume that I'm going to take this value minus this one. So definitely, if I take this minus this, what is going to happen is that, see, if I calculate the slope here, so you know let me just remind you people of some small primary school arithmetics. I'm not going to go deep into the maths, but let me just give you some small primary school arithmetics. So in primary school, you people studied something like this. You said m, which is your gradient, is equals to change in y. The way I wrote my change is like a. If you go back, they'll say they used to write change like this: change in y over change in x. What they mean by change in y is that if I decide to calculate the slope, so if I have a line like this, and I want to calculate the slope of this line, let me say I want to calculate the slope of this line around this area. I'm just going to pick a point around this area, this point, and then I take, so this is going to be my gradient, right? So I'll take this point, and then I take this point. So this is the gradient around this point. That's the gradient. So what I'm going to take is the value of y. This is y and x. So what I mean by changing y is that I'm going to take the value of x. Let's say this, if you start from 0 here, and then this is like 5, let's say 10. And then here, you start from 0, this x should be like, say, 2, and let's say something like 4. It can be 6, 8, 10, and all of that, right? So let's calculate the change in y over change in x. What we are calling the gradient is that you're going to have 10 minus 5 over 4 minus 2. And if you do this division, you're going to have 5 over 2. This will now give you the gradient around this point. Makes sense to you, right? So now that I've explained that to you and you understand what I mean by the gradient. So what the algorithm will do is that you say, if I pick a random value of b, for example, if I start with a random value of b, then what I'm going to do is that I'm going to see where that random value of b meets my plot. And what I do there is that I'm going to calculate the gradient at that point. Mind you, look at what is going to happen. Pay close attention. If I do the gradient here, so let me clear this. Let me just clear this so that I make it clean for my us to understand what we are talking about here. I can just clear this one down after I know you understood what I said. So let me clean this one because I don't want to go writing a lot of stuff, right? Yeah. Okay. Over. Let me have my change in X again written. And so here I'm going to draw my graph. Somebody help me put a square here. Thank you, Do. So now, once I want to calculate, let's say this was our point of B and we calculated and we had our point here. So we are calculating the gradient around here. So to calculate the gradient around here, we're going to take the slope. So it's going to be the change around this point. So we're going to take this value here. The value of Y here, let's say this is Y3, and here is Y1. And then we're going to get the corresponding value of X, right? The corresponding value of X is X1 and say X3, right? So now we are going to say that the value of M for this random value of D, M, will be equals to Y3 minus, wrong writing. It's going to be Y3 minus Y1 all over X3 minus X1. I don't like going into this deep mathematics because not everyone here is a mathematician, but let's just do this for the sake of understanding, okay? And if you look at this, normally, if you understand this plane, you notice that Y3 is greater than Y. So we can put 10, 5 here, and then we put 2 and 4, just like we did before. So if we do that, we're going to have 10 minus 5 over, so here is 5, here is 10, here is 2, here is 4. So we have 10 minus 5 over 4 minus 2. And if my mathematics is correct, very well, this will give me something like 2.5, right? This is a positive value. Can I get somebody to be talking to? If you know that you don't like maths, please put your hand up, let me know. You'll be the person I'll be talking to.
Hello, sir.
Dr. Kifa.
Yes, sir.
You are the one who doesn't like maths.
No, but I'm trying to follow.
Okay, well, so now that you indicated, it's fine. You'll still understand, okay?
Yeah.
I
want to ask something.
Yes, please go ahead.
Yeah, if the slope of the graph is in the negative direction, for example, when we were talking about the correlation, if it is sloping down, and then the one that is sloping upwards, when you calculate this gradient, the one sloping down will be negative, or there will be no sign attached to it. Like the one you've just calculated now with the tangent that you wrote, it is sloping downwards. So I was expecting that it will be a negative at the end, maybe 5 minus 10 or something.
Let's just pay attention, and then we're gonna see what we get, right? Just be patient, and please don't mute yourself because we're gonna have a very long discussion in line with that. Is that okay? To see how the gradient descent functions. Is that okay? Just stay put. And if that was the same question you have, please just follow the discussion as we go along, and you'll find yourself fitting in along the way. Is that clear?
All right, sir.
Okay, now let's have a discussion, Dr. Gifa. So, like you rightly pointed out, what's the sign of this gradient here? It's positive. It's positive, right?
Yes.
Yeah. So we are saying that if I calculate the gradient around this point, it's positive. Is that correct?
Yes.
But I know that my minimum is down here. This is where I'm looking at, right?
Yes.
So if my initial value of X that I picked was here, and it landed here, and it gave me a slope that is positive, and my target is to get here, do I need to add the value of X, or I need to reduce the value of X? Remember, it starts by picking any random value of X and then calculating the slope around where that value of X meets the plot. So my question is, if this was my initial value of X that I picked, right? and it made the slope of here, and I calculated the value, and I calculated the slope around this point, and it gives me positive 2.5. Now, if I want to, if my target is to come here, the next value of X that I'm going to pick, should it be an addition to the initial one, or it should be a subtraction from the initial one?
Addition.
Okay, good. So that means if the, so now you say it's an addition, right? It's okay, it's fine, right?
Yes.
So now I'm going to do another thing. Let's calculate, let's assume that I add. So let's assume this is, let's say, well, let's say the value of, let's say the value we pick here was what? What did we say here? Let's assume that this value was 2.
Yeah.
And then I add, and but when you said add, did you give me a specific number to add? You did not give me a specific number to add. Let me say I add 10. Where would 10 take me to? To around 12 over here, right?
Yes.
So let's calculate, let's come and see where it meets the one. This is where it meets the this thing, right?
Yes.
Is that clear?
Yes.
So now, if we come here now, we also, and I know I didn't draw this thing well. I don't know. If I drew this thing well, you would have noticed that. Yes, Mr. Tony.
Yeah, is it possible to add a highlighter to what you are showing? Maybe as you are, although as you are here, maybe for us to really see when we are saying this is Y3, or just a highlighter, as you are going out. I don't know if this software have something like, because I find it difficult to follow you when you are showing this thing. I don't know if you understand.
Is it that you're not seeing my screen, or you cannot follow the narrative? Let me just.
Yes. I'm seeing.
Right.
Yeah, I'm seeing your screen. I'm seeing. Yes,
Clearly.
I'm seeing your screen, but like, yes, clearly. But when you say you add 10, you do this one. I'm trying to follow. The this thing that you are doing, but so I'm just saying, I don't know if the software have something like a highlighter, so that as you are going, you highlight to see where you are. And
maybe I can change the colors when I'm writing this. I change the color to another one. Would it help? Yes.
I think he can just follow where your name is, because it's your name tag that gives where you are.
Yeah, but sometimes it's difficult to. Yeah, I understand that, but sometimes
I understand Mr. Tony's problem. Mr. Tony, this is an interactive board. You can move this board left and right based on. If you cannot see where I'm writing, please try to try to move your mouse. Use your mouse to change the position of the board, because again, as I'm writing, I'm going like Dr. Kifa Riley pointed out. I don't know if Benito who pointed out. It follows. If you see where I'm writing my name, you see my name. If I've gone right down into your computer and you're not seeing what I'm writing, you have to move your board up to be able to see what I'm writing. That's why I said it's an interactive board. You have to be able to move it. If you cannot move it, you will not follow me, because there are times I will be writing, but you will not be seeing where I'm writing, because I've actually pushed. Because my own, I can actually push my own. As you can see, I'm pushing my own. But if I'm pushing my own, you are not seeing that I'm pushing my own. Right? Because I'm pushing it up and down, but it's not moving at your end that I'm pushing it up and down. You have to push your own yourself. I don't know if you understand what I'm saying.
No, I understand all that. Maybe I've not found the right this thing to explain here, but we can continue.
In another sense, if you're following, maybe if I'm changing the colors of what I'm writing and pointing out, maybe it can help you. I don't know, because now I'm talking about 10, I'm talking about 2. Maybe if I were writing in different colors,
I think
maybe for example, I'm now writing, I'm indicating my 10 with the red. Can you see my 10 with the red?
12. Yes, we can see.
Beautiful. Now we are. You see. That kind of thing. That's what I was talking about.
And like this, like I'm just coming back. I wanted to point out something here, and it's very important, because like Dr. Kifa was trying to ask, if I draw my line like this, if I draw a line like this, and I draw a line like this, if I want to calculate the gradient of one of these lines should be negative, right? So now the question is, which of these gradients is going to be negative? Is it this one? Or is it this one?
That was a question.
Yeah, that's what I want to figure out. So this brings me to something. Let me pull it out because I need to use that concept to explain this. This is what I'm trying to explain here. Negative and positive gradient. I want to see something. Okay, give me a minute. Let me pull it out. Blah, 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 blah. Okay.
Hey, have you watched? You watched it there. Ça va. Yeah, bro, see this. Increase. Pass cover
Who is that?
Pass cover the DT. You watch now 3 egg there. Pass go watch. Nonsense DT man.
Benito.
Benito. You are the one who is insulting people that they have not beat. Please give me a minute. Let me get this thing. So you get this. It's working. They call it positive. Again, no one is giving me a very perfect explanation as to why they are calling the gradient negative and positive. That's the explanation I'm looking for. They are just telling me that if it is like this, it's negative, and it's like that's positive. How do you show that? Oh, okay. It's at the level of change in X. Oh. Now, if you take this one like this, change this one like this. Let me see. Give me a minute. Let me just sort this thing out just to be sure that my explanations tie with the intentions. Let me not explain something and then I'm having something. Where is that? This should be positive. Where's the negative guy? You ain't showing me a negative guy anyway. Oh, this is a negative guy. And this should be this minus this. And again, you're not showing me how negative it is. What makes it negative? I know it's at the level of change on the x-axis, so I'm trying to figure out. Can you see what I'm getting here? These guys are telling me is that if I have a plot like this, and if the gradient is like this, it's a positive gradient, and if the gradient is like this, it's a negative gradient. And I'm just trying to figure out where the negativity comes, because if I want to calculate the gradient here, as I'm trying to understand, this is going to be, this is x1 and x2. If I want to calculate the gradient here, oh, okay, I got you.
Hello, sir.
Yes, Mr. What's that? Sorry, I'm not looking at my screen. So, yeah, please ask your question or help me out with the identification of the gradient sign.
Yeah, I want to believe what makes the other one sloping downwards is the is the y, the change in y, because as x is increasing, or as x increases, y is instead decreasing. So if we start with a bigger y and you're coming down, as x increases, the y is dropping, so it will be a negative at the level of y. So you take the negative y divided by x, you have a negative value.
That's pretty clear, and I'm trying to understand that, right? So I'm trying to, that's what I need that to be able to explain this concept over here. I need to make that pretty clear. So let's call this y2, y1, right? Is that correct to say so? Is it correct to say y2, y1, x1, and x2, x1, x2? And so this was going to be change in y over change in x. And if it's change in y over change in x, again, I'm trying to get it right? I'm trying to get it right. And so if we start by saying y2 minus y1, again, we're going to get it wrong, right? Do you see that?
For me, it will not be wrong, because
if I do this here and I get x2 minus x1 again, it's going to be wrong. It's not going to be negative, right? This is and this. Definitely, if this is moving like this, they'll end up being positive. But one of these is supposed to be negative. I don't know. Maybe I'm thinking of it wrongly. If you can figure it out, it's going to help me a lot.
So, when you look at the value of y2, you discover that it goes to x1.
Pardon?
And
oh, yeah. This is supposed to be x2 and then x1. Is that what you're saying? Yeah, that's correct.
Yeah. That's it.
Okay, then that makes sense now. Thank you. And therefore means, yeah, that makes sense now. That makes sense now. Okay, great. So I had to come back here and make sure I figure this thing out, right? Clearly. So now, you notice here now that if I want to plot, so what we are saying is that if you look at the way we are explaining this gradient here, for those that did not understand, this is y2, x2, y1, x1. This is y2, x2, y1, x1, right? So you notice that, if you notice here, you notice that the value of x2 and x2 is smaller than x1, which makes sense, right? For a negative, this one is negative. This one is negative and this one is positive. Because if you notice here, when the value, if you notice on this, if the value of x is increasing, like if you take this, normally this is 0, this is 1, 2, and then it goes up 3, 4, and then but then this is 0, this is 1, 2, 3, and then it goes up. And then you notice that once the value of x is instead increasing, the value of y is instead decreasing. Look at x2, look at where it comes to y. Look at y1, look at when it comes to y. So you notice that as x is increasing, y is decreasing, and vice versa. This is a negative relationship and this is a positive relationship. So we are saying that what gradient descent does is that the algorithm will pick a random value of b, and then wherever it plots, it meets the y-axis. Wherever it meets the plot, like if it meets the plot here, it's going to calculate the gradient at this point. And if you calculate the gradient at this point, you notice this gradient is going to be a negative gradient. Yeah. And then if it plots it, and then if it meets this, if it plots the gradient at this point, you notice that this gradient is going to be a positive gradient. And this one is going to be a negative gradient from this explanation I just gave down here. This is positive, this one like this is positive, and this one like this is negative. And so you notice that if you calculate the value of the gradient, then this was going to give us negative 2.5. And if you calculate the value of the gradient, you will notice that if the value of the gradient, this is where it's important. If the value of the gradient is negative, look at it, that means this is where it is. And so if it is negative and it's here and its target is to come here, and the target is to come here. So the question is, how do you move from here to here? What happens to the value of B? This was the initial value of B that you chose. So do you now move like this, or you move like this to get here? And like Dr. Kifarani pointed out, for you to move from here to somewhere around here, you have to add the value of B. So it will add the value of B based on the sign it gets from the gradient. So if the gradient is negative, it's going to add the value of B to the existing value. And once it does that, it's going to calculate the gradient of the new point. And that's why I've said that if you add the value of B and it now skips this point and come here, you'll notice that it will calculate the gradient again at this point, and the gradient now will now go down to what? Positive. And once the gradient is positive, what it's going to do is that it's going to reduce the value of B. And so if I bring down my graph and then I plot a new positive graph, you'll notice that this is what we have. So I'm going to show my target with black. This is my target. This is where we want to be. And so when it started, let me change this to maybe, no, let me change this to maybe this funny color. The initial value of B1, this was B1. And so it calculated, and B1 made the point here. This is the point B1. This is where B1 meets the graph. And it calculates the gradient here. This gradient here is negative. So notice that for me to get to, so let's call this uppercase B, capital B, which is our target where we want to go to, because this is where the error is minimum. Notice that this is the error. This is where the error is minimum. So its target is to come here. And so if it picks, initially it starts by picking any value of B. And so it picks a random value. And if it picks a random value of B, let's say B1, it looks at where B1 meets the curve. And if the value of the sign in front of the gradient at that point is negative, it is going to add. So it's going to pick another value of B. But then when it's picking the other value of B, it's going to make an addition. Like it's going to now say, I'm picking a bigger value of B. Is that clear? Now let's assume that you want to pick B2 and it goes and add a very big number, and B2 now comes over here, B2. Then it comes here and it calculates. You see that B2 meets it here. And you see that at the level of B2, we have a positive gradient. And again, it has skipped the target. So what does it do? What it has to do is that it needs to reduce the value of B2 and then come to, so that before it gets to this target where we are. So you notice that what would have really been ideal is that if it picks an initial value of B1 and then defines it here, what it should do is that it should move small steps like this and be coming down and be coming down and be coming down till it gets here. But you notice that no, that was not what the guy did. The guy moved from here and zoomed here. You understand? This is not what we want. So to solve this problem where it will not move from here and jump here, they introduce a constant, and that constant is called what we call the learning rate. The learning rate. And so when you put the learning rate, we are going to see how, when we go to the practical session, which is going to be in our next class, I'm going to show you how the learning rate affects the movement of this thing from here to here. You notice that when you introduce the learning rate, instead of it moving from here to here, it now goes down gradually until it gets to the point where the error is minimum and picks the value of B. And you notice that once it picks the value of B here, and you notice something, I want you to pay close attention. Here, if the error here is not negative, and you notice that at the point where the value of B, where the error is negative, if you notice carefully, the gradient is also 0. Is that true?
Yes, it's true.
There's no gradient here because this is almost like a straight line. Unlike this one, you cannot see whether the gradient is positive or the gradient is negative. So what gradient descent does is that instead of doing what OLS does by just plotting the error against B, keeping M constant and then looking for the minimum and doing the opposite and then taking the two values of B and X and then plotting, then putting it in the equation and getting the equation of the line, which is going to be the line of best fit. What gradient descent does is that it rather starts with a random value of B, and then with that random value of B, it starts calculating the gradient. Once it calculates the gradient, B, due to the sign, given the sign that it gets from the gradient, it now uses that sign to know whether I'm going to add to the existing value of B that I picked, or I'm going to reduce from the existing value of B that I picked to be able to get to the solution of that is best. Is that clear? There's a lot of mathematics. There's a lot of mathematics here. Integration and differentiations, and you're calculating to and fro. I don't want to come in with that here and scare people. But this is how gradient descent functions. This is the, how do you call it, for the people who know a lot of big book, it's called the modus operandi of gradient descent. I noticed that it's different. And so in this case now, if we had multiple, it is not going to be a problem, right? So it doesn't matter if I pick the value of B and it falls here, I don't care. All is that I calculate the gradient here, and wherever it falls, I begin to move to and fro and find myself to where I get the minimum error, and I pick that value of B at that point. Is that clear?
Yes.
Is there any question? Oh, those people who did not understand, put your hands up. If you do not understand, please put your hand up. Nobody's putting their hand up. I think that all of you understand.
Me, I'm a bit lost, but I don't even know where to start asking the question from. But I think with time, I will catch up with the whole mathematics thing.
I did not even bring the mathematics, Mr. Tony, because if I brought it, a lot of people would have just dropped from the call. We started the call, we were how many? We are 7. If I bring mathematics, only 3 will be left. So I just explained it in the most simpler way. Actually, there is some math. What happens is that this is not just doing it by the way I'm showing it, telling you that it moves like this. There's mathematics. It calculates the gradient, it calculates the gradient. Like, if you notice, just because now that we are saying it, let me bring in a bit of something to say something, right? If you notice now, if you notice what happens is that once it's calculating the formula to get the new value of B, this is the initial value of B when it guesses B1. The formula to get B new, which is B new, the new value of B is equals to B old, let me call this B old, minus the slope. Minus the slope, then when it does minus the slope, and then that is how it gets you see there's some mathematics here. So it says B old minus the slope. And they say, and then now this is now what you need to understand in mathematics is that the way I was calculating gradient, this is not how mathematics, they don't, if I say gradient, how you calculate gradient is that gradient is the derivative. So, oh God, this is where I did not want to go to, but let me explain. If I have my equation of line, assuming my equation of line is y equals to mx plus b, right? How you get this one is by differentiating this equation, dy dx of mx plus b, right? And if you differentiate this equation, you end up having dy dx of this equation is m. For those people who did small mathematics, is that true? If you differentiate this equation, you end up with this, because if you differentiate m of x, if you were integration, would have had mx squared plus, I think, is it plus mx squared, something like that. But if you differentiate, you end up with I think m or something like that. So there is a so this is how you calculate the slope, by differentiating the equation of the line. That's how you calculate, and then you take the BO, which was the initial value of B that it gets, minus that slope to get the new value of B that you are going to use. And now that I said that there is something called the learning rate, what is going to happen is that it's going to do this so it's going to do this by doing this. So once it wants to introduce the learning rate, it introduces the learning rate to this equation. So a learning rate is a constant and it's not any value, it's any value. So you have B new now becomes B old minus learning rate. Learning rate multiplied by the slope. And I think there's actually a way to show you this in but if I have to show you this, maybe I'll have to let's hold on, let me try to show you this in a more holistic approach, so that I don't have people coming after me. So let me see if I can get a more suitable equation of line here, right, that I can use.
It's now that I know why a lot of people are not doing data science.
I know it's very simple, right? Like I used to tell you, right? It's more about you understanding the ideas that run in the background, and not just me just telling you that, oh, it does this, it does that. I'm trying to get a more suitable equation. Let me see and get an equation of line. Let me see. Okay. If I differentiate this equation, I get okay. Let's do an assumption, right? Let's say my equation of line. Let's say my equation of line is y equals to mx plus b. Now, what happens is that, please, this mathematics is not strong. I will not go show you how to do differentiation, but I'll just tell you what is going to happen. Let's say it's mx squared plus b. Now, what is going to happen is that it's going to assume a value for, it's going to first of all assume a value for b, any value. Let's say it takes 3, so you are going to have y equals to mx squared plus 3. That's the value of b that we are talking about. So now what is going to happen is that it's going to calculate this by differentiating this equation. And so what it happens is that if you differentiate this equation, what you're going to end up with is that you're going to end up with mx. If you differentiate this equation, you are going to end up with just mx, right? That's going to just be your mx. And so
It's a 2mx.
What is that? 2mx, yes, 2mx. And so if you now go and get, and you want to get the value of b new, so we say b new. So this is going to be our gradient, right? And so if you do this, let's say the value of x, is so how do we do this? I'm looking at the possibility of saying that the value of x is same. So once we calculated the slope down that time, what was it? Was it minus 2.5? So now let's say in our prediction we're gonna have x. Let's say x is 8, and then and our slope is 2.5. So we're going to have something like 8 into minus 2.5, right? And if you calculate this outcome, you're going to have your slope. You're going to have, how do I put this? Let me put this in a more constructive way. I don't want to get the whole thing twisted out so that people get the whole thing missing. So I'm looking for a more convenient equation. Let me just see some equations online and which one is better. And then I see. Okay, I think I see a more better equation that can make sense. Let's say an equation like y equals to 4x squared plus 3 was our objective function. This is what we call our objective function. This was our objective function. Let's say this was our objective function. If I differentiate this equation, dy, dx, please don't look at me. If you differentiate this equation, you are going to have 8x. This is going to be the differential of this equation, right? And so now, this is going to be this is what is going to be the output of this. Don't ask me how this is done. That's what we already know from small maths. So now, if we take a value of x, and so this is going to be our slope. So if we come down and we have we come and calculate our slope that time. And so we take, when you want to calculate your slope, we calculated our slope that time. It was, let's say minus, if you say x in this case, let's say x is minus 2, or let's say x is, I don't know, can be any value. So let's say our x value is 2, minus 2 or something, or 2. If you put minus 2 here, you have 8 into minus 2, and this gives our slope to be minus 16, right? This is going to be minus 16. So now, if this our slope is minus 16, because remember, when you have a point, your point is always 2, 4. That's what I'm saying. If you have a point, this is the x value and this is the y value. So if I have a point -2, maybe 4, this is the x I'm talking about. So I take that x and I put it here. I have 8x. So that's what I'm putting, and then I have -16. And so now, if I come and I say b new is equals to b old minus b new by b old minus slope, sorry. That means if I choose a random value of x, say 3, and then I want to get the b new, because I chose 3 over here, right? It was 3. Yeah. If I say b new now is equals to b old, which is 3 minus 16, and you notice that if I get my new value of b new now should be equals to, this should be what, 18, right? You'll notice that if you had this plot was like this, if your plot was like this, for some reason, let's see, we have, sorry, this is not plotting, you have this thing like this. Let's just say it's running like this. Or if I draw this one, it's gonna confuse you. So let me just draw one loop. Let me draw just one loop. Let me say we just had one loop like this. Yeah. Let me say one loop like this. I understand that if my b new, let's say I had -2 here and I plot it here, and then it was here, I know that it has jumped from -2 to what, 18. That means 18 is somewhere over here. So you see, it has made one big jump like this from -2 to 18. Is a very big difference. but you wanted a way that it can come down small. So now let's take a learning rate. Let's say our learning rate now is, let's take a learning rate like 0.2. Let's take a learning rate like 0.2 or 0.1, right? Or even if you can take a learning rate to be anything, take a learning rate to be anything. So can somebody, if you notice that if this is -2, you know that 0 is somewhere around here. For those who know the number line, you know that 0 is somewhere around here, and then this -2, 18 is up here. In between 18, there is 0 in the middle. So can somebody just do this multiplication, assuming that we take a learning rate of 0.2, we are going to have our B new is equals to, what is that? 3 minus learning rate, which is 0.2. So we have 0 minus 0.2 multiplied by -16. Can somebody do this multiplication and give me the value, please? Can you give me the result here?
So 6.2.
Pardon?
6.2.
6.2. So B new is equals to 6.2. Do you see that 6.2? This was 18 here. 18 here. Let's even increase the learning rate to 0.01. B new is equals to 0. Let's say the learning rate is 0.01. Can you try 0.01, please? 0.01. Try 0.01. 0.01 times -16, and then take 3 minus that result. 3 plus that result, shall we? 3 minus, I mean, if you want to be negative, whatever. Can you just give me that value? Let's see where we go to from there. Can I get an answer?
3.16.
What's that? 3.16, right?
Yes.
So let me show you now what this means. It means that if I had my point like this was my graph, this was my B old was here. If I don't have a learning rate, my B new will be 18. My B new will be what? 18. Is that true? So it has moved from here to here. It has passed my point down here. This is my target down here. It has passed my target down here and jump over here. Now, when I added learning rate of 0.2, it takes me, instead of coming right over here, it takes me somewhere around 6. So let's say if this is 18, 6 will be somewhere around here, right?
Yes.
It takes me somewhere around 6. Where's 6? This will be 6. And if my learning rate is 0.01, it takes me somewhere around here, which is what? 3.16. So this one gives me 6.2. You notice that with the learning rate, the jump is smaller. Look at the first time when I had no learning rate, the jump was big. The second time when I had a bigger learning rate, the jump is like this. So if I take 0.001, can you try 0.001? 0.02, the jump is like this. 0.01, the jump is like this. Can you try 0.001, please?
It's 3.016.
3.016. Did you use 0.01?
Yes.
0.00, like 2 zeros, or you can make
Yes,
3
sir.
zeros.
Yes, sir.
But
Yes, sir, it's a
add it,
3.016.
yeah, add it to 3 zeros, like 3.000, like increase it. Let's see whether it's going to be more. I want something that will fall somewhere around here. Do you get something?
Yes, it will be
And you notice that
3.0016.
it's just increasing. And now you notice that, and this is so nice. Now notice The moment I keep the learning rate, as it's getting to the solution, do you notice that as it's getting to the solution, the difference is not becoming huge again?
Yes.
As it's getting to the solution now, you are now moving to the other one you told me was 3.16. The other one is 3.006. So it's just small, minor steps, right? As it's approaching the solution, you notice that the steps are not getting big again. Because the reason is because, and trust me, if you keep changing this value, it will come a time where it will just be dancing almost around the same area where the difference will not be huge. And then until you notice that the difference is completely insignificant, that would have brought you closer, that would have brought you to the solution where your value is, where your error is minimal. Is that clear? So you got that small jump. Now you start making small jump. So that's where the learning rate comes in to solve that problem for you calculating PNU, so that it doesn't keep jumping to and fro. Because when you came to 18, if you now want to reduce, you say you want to reduce now so that you come down here. You don't know what to reduce again. You are not careful, you want to reduce again, it jumps down here. So now you notice now, I want to show you something, because when we go to the practical lessons, you're going to see. You notice the number of times we have done this, we have calculated PNU. How many times? Calculated PNU 1, 2, 3, 4, maybe 5 or 6 times, right?
Yes.
This is a loop. This is a loop. And this is the number of times. You remember we used to say for I in range. For I in range, right? I used to give you a loop like in range. Let's say 10. This means if I do this, I'm telling this thing to do this loop 10 times. And notice the relationship between the learning rate and the number of loops. When my learning rate was 0.2, what happened? It moved down here, very down here. So what I'm saying is that if the learning rate, let me call it LR, is big, the number of iterations reduce. Number of iterations, please take this seriously. The number of iterations reduce. This is an interview question. And if the learning rate is small, the number of iterations will increase. Like you need to loop many times before you get to the solution. Do you understand? Compare. I want you to compare. When my learning rate was when I started my learning rate was 0.2, you notice that it moved from 18 to 6.2. When I moved my learning rate to 0.01, it moved from 6.2 to 3.1. What's the difference between this and this? This difference and this one is not the same. Right? That means if I wanted to get the solution faster, I'll use a bigger learning rate. That means I'll not loop many times. And if you want to try it, let's keep the learning rate at 0.02 and see something. Let's try. Let's go. So if I use 0.02, I would have it would have given me my 6.2, right? So I'm saying that my B would have been equals to what? 6.2. Now, if I come here now and I say my Y is equals to 4x squared plus 4x squared plus B, right? That would have been that my Y is equals to 4x squared plus 6.2. This is my B now. And if I differentiate this equation and I'm using my Y as -2, this would have meant that if I differentiate this equation, I would have had, it will bring me back to -16, right? -16. It will bring me back to -16. And so now if I have -16, that is my slope. And then my learning curve, remember my learning rate is 0.2. And then if I want to calculate my B new again, my next B new, this B new, the next B new now will be equals to, now I would have B old, which is 6.2, minus my learning rate, which is 0.2, multiplied by the slope, which is -16, right? And so if you do, can you calculate this value for me, please? You'll notice that it will jump closer to, it will be coming down. It will be coming from up here like this. It will be shifting down like this. You see that we'll move from here to somewhere around here. Then we are coming to somewhere around here.
9.
Somebody should punch this. What's that?
9.4.
Are you sure that it's 9? 0.4. Can somebody punch it again? This is 0.2, please. It should. I
Okay,
expect it to be
9.4.
shifting down, not. I expect it to be shifting down and not going up again.
Okay, it's
I
9.4.
expect it to be shifting. Can we do this again? Can you do what did we have here? 3 minus. Can I get 3 minus 0.2 multiplied by negative 16? What was this value, please? You said it was 6 point something. I'm getting a different value now. It's getting me a little confused. It shouldn't be. This value should not be less than this one. That's what I'm saying. Normal, right? Because this is a constant, and 3 minus this constant should not be greater than 6 minus that constant. Should not be less than 6 minus that constant. It doesn't make sense. I don't know if you're getting what I'm saying. Punch this, please. Can I get this value? I mean, negative. Yeah, this one should be bigger. Maybe let me just see. Yeah, please, let's get this value just to be sure that it's moved. It should take us to the same place. Let me see, what, 6.2, 6.2, 6.2. Yeah, this is gonna sum up to addition. And then this again, it's gonna go bigger.
Yeah, because it's addition.
Yeah,
So
because
this
it's
is bigger
addition,
because
so it's gonna go bigger. Yeah, it's gonna go bigger because it's addition, right?
Yeah. But the other value was
And
3
so
and
again,
1
let's
6,
come.
so
Pardon?
If
I
the
think the
value
other
is
value was 3 and 1. So when I add, it's going to be larger.
Yeah. So it should go bigger because it's a negative value. That gets me some point. And so I think the problem is that because of this, something was going to change over here. What was that? I was going to get something was going to change. Was this going to be the equation of the line that was going to change? Was it the gradient that was going to change? I think it had to affect the gradient. I'm just trying to figure out where it fit in. But the truth is that normal, what works is that this first value should be up here, the second value should be down here, the third value should be down here. So as you keep iterating, it keeps coming down. As you keep calculating B new, it keeps coming down till you come close to somewhere here. And that is, let me see. Let me just make sense out of all of that and see how the equations moves online. Was that not supposed to be instituted into? Oh yeah, that's because, yeah, I get it. It's because this function is supposed to be, this objective function is supposed to be a function of B, right? It's supposed to be, it's supposed to be a function of B, because if I do, let me see something. If you take, if you take the value of 6.2 that we had here and substitute it within, so you're gonna have, should be 8 minus, what was our new slope that we had?
negative 16.
I know it's not supposed to be negative 16, right? This is what I'm saying. See, please, we are getting it all wrong. So our new, when we calculated these, where's that? When we calculated, where's that? Let me just remind ourselves, please. That's where we are getting it wrong. It's not supposed to be. So you remember, we started here like this, and we calculated our slope here, and our slope here was what, negative 16, right? Negative 16, is that correct?
Yes.
Right? And so we added, and so we moved from negative 16 to stay somewhere around here, which gave us 6 point, what was that? 6.1. This slope here should not be negative 16 again. Is that correct? This slope, we cannot use negative 16 here as the slope again, is wrong. Because the slope here was negative 16, doesn't make the slope here negative 16. So we have to recalculate the slope at this level.
Okay.
Right?
Yes.
Is it making sense?
Yes.
Yes, sir.
Nobody's understanding what I'm saying. The slope
Yeah,
here,
it
when we
makes sense.
started, we said y was equals to 4x squared plus b, and our b was 3, right? This was our equation because we started here and our b was 3. So we differentiated this equation, and then we got the slope here, right?
Okay.
We got the slope, and then we replace the value of b, right? So now that our equation has moved from here to here, the slope cannot still be the same. It cannot still be the same slope that we had here. The slope here and here cannot be the same, right? Can you all follow?
Yes, sir.
Sorry, my network kicked me out. Can you all hear me? Can
Yes.
everyone hear me?
Yes, sir. Welcome back.
Can you all hear me, please? I can't get any response from anyone. If you can hear me, please, let me get your response.
I can hear you.
Okay, great. So I was trying to say that our slope cannot be the same as the same slope that we had there, right? We cannot be the same. So because our slope was from here to here, we move from here to here. So the slope here cannot be the same. So if we take the slope here and then we take b nu, assuming that the slope here is going to be positive for some reason, it's going to be a positive slope. So let's say the slope here can be like 4 or so. So if our b nu, so we're going to have our b nu now, b nu will be equals to b old, which is 6.2, right? 6.2 minus learning rate, which was 0.2, multiplied by the slope, which is 4. This slope here and the slope here is not the same. This is given a positive slope and this is a negative. So can we get the value here, please? Can somebody just multiply the 6.2 minus this? This should give us a smaller value from 6.2. I'm positive about it. What did we get?
The 5.4.
Said it. It should give you 5.4, right? 5.4.
Yeah.
And so you notice that if we keep running the iterations again, if this slope, if you notice that and I showed you that as you are moving towards this, the slope is reducing, because if I move from here, if I come down to 5.4 here, 5.4 here, the slope here should be smaller than the slope here. Is that true? The slope over
Yes.
here is steeper, and if I come down here, the slope will be smaller. So let's assume that the slope goes down to 2, and you put 2 here. What is going to be the new value? And then that will mean 5.4 minus that value, please. 5.4 minus this new value. Don't use 6.2. 0.2 multiplied by 2, you should give you a value. Again, that value should be less than. What did we get?
5.
What? We get 5. 5.0, right? Again, and you notice that we keep, and if we go down again, if you calculate the gradient to come down here, let's assume now that the gradient now is 1. Please pay close attention. If you calculate the gradient that comes out, let's assume that is 1, then we're going to have, here we're going to have 5.0 minus 0.2 into 1. Can we get this value, please?
4.8.
4.8.
4.8.
4.8. Now, I want you to take close. Let's do a sequence. We move from 6.2 to 5.4 to 5.0 to 4.8. Can somebody calculate the difference between these, all of these? Can you calculate the steady difference? 6.8 minus 6.2 minus 5.4. What is the difference here?
0.8.
What?
0.8.
0.8.
0.8.
What's the difference here? 5.4 minus, this should be 0.4. And what's the difference here? 0.2. What's the difference here? 0.2, right?
Yes.
You notice that as we move closer, as we are moving closer to the solution, the difference is reducing. Are you seeing?
Yes.
That means you come, and that is the reason why you will never come and jump this point. Because as you keep coming down, this will be going down. And if you calculate the next value, it will go down again. It will go down to about 4.6 or 4 point something, right? Up until when you come to you will notice that, like tomorrow when we see the practicals, you notice that when you're coming to when you get a solution, the difference becomes insignificant. That means this difference now will goes to something like 0.000000001 or something. And then by then you can know that at this point, this difference is insignificant, and you can consider that point as your solution. Is that clear?
Yes, sir.
So the only thing that is left is a practical session for gradient descent, which we're gonna have that on Thursday, hopefully. And then after that now, we can move into some other topics. Is there any question or any doubt? Please, if you can try to check some material online, maybe watch some videos, maybe my own explanation was not going the way you understand. Try to watch some videos online about gradient descent. You're going to get the same concept, but maybe explained in a different way that makes it more easier for you to grasp the concept. But just to understand that, what happens for gradient descent, just to summarize, is that once your algorithm is using gradient descent, what it does is that it gets a random value of B. Once it gets that random value of B, it plots that random value of B and gets the gradient at the point where you have B. If the gradient is negative, it adds the value of B. If it's positive, it reduces the value of B. And how does it reduce? It uses B new is equals to B old minus a learning rate multiplied by the slope of the line. This is what it does. That's how it does it. And with this, it now uses this, that, and then it has to do this over and over a number of iterations. And that is called epochs. They call them the number of epochs. I don't know if this is how they spell it, or is it why epochs? And you have to, when you notice that tomorrow when we are customizing the linear regression model, we will give this value of B where we want to start. We'll specify the learning rate, and we'll specify the number of epochs, like the number of iterations that we want to perform. And we'll even do what we call hyperparameter tuning. where we now say we don't know the best number of epochs, they know the best number of iterations that will give us the best solutions, and we don't know the best learning rate. So we are going to now give a range that is going to use, say, let's say a range from say 0 to say 10, for example, for learning rate, and a range from maybe 10 to 100 for the number of epochs, to be able to say it's going to run this loop this number of times to get to the best solution. We're going to see all of that in play tomorrow. Is that clear? The practicals I like the practicals for gradient descent because it's so nice and straightforward. You see the solutions playing out. Okay, that's it. We're going to keep it like that for today, and we're going to continue on Thursday, okay?
Okay,
Bye-bye.
sir. Good night.
Good night.